Now, here's the method for calculating empirical formulas. Basically, empirical formulas are often calculated as chemists are trying to identify chemicals. So here's an example problem for that. A substance is tested, and while it's tested in a lab, we discover that it has a percent composition of 50.91% zinc, 16.04% phosphorus, and 33.05% oxygen. So from that, we need to calculate the empirical formula for this substance. Okay, so we've got a process to go through here. Steps to answer empirical formula questions. What we'll do is we'll first convert the percentage composition data into mass data by assuming that we've got a total sample mass of 100 grams. So let's go ahead and do that first. So go down here, first, okay, so for a 100 gram sample of this substance, there's going to be zinc, and zinc makes up, we said, 50.91% of that sample. So multiply that by 100 grams. In total, zinc is going to make up 50.91 grams of the 100 gram sample. For phosphorus, it makes up 16.04% of the mass. So in 100 grams, we're going to have 16.04 grams. For oxygen, we have 33.05% of the mass, and so that gives us 33.05 grams per 100 gram sample. Okay, so that's step one. Step two says to determine the number of moles of each element in the sample, the 100 gram sample, by dividing the mass that we have of each material by the molar mass of each of these elements. Okay, so let's go ahead and do that. Number two here. We take zinc. And for zinc, we discovered that we've got 50.91 grams of it in that 100 gram sample. We will divide by the molar mass of zinc, and if I look it up in the periodic table, I'll find that zinc has a molar mass of 65.38 grams per mole. The unit up here was grams. Okay, so that works out to be, using my calculator, 0.7787 moles of zinc in a 100 gram sample. Doing phosphorus now. Phosphorus, we said we had 16.04 grams. Divided by the molar mass of phosphorus. If we look up phosphorus in the periodic table, we find that its mass is 30.97 grams per mole. Okay, and so the total number of moles that we get for phosphorus in a 100 gram sample is 0.5179 moles. Moving forward, for oxygen, we said that our sample would have 33.05 grams. Divide that by the molar mass of oxygen. It is 16.00 grams per mole, and that works out to be 2.066 moles. Okay, make a little space here. So basically, now that we have those amounts of moles, to start to set up our empirical formula, we can write down that the formula is going to be something like zinc 0.7787, and we normally wouldn't want to do this. We want whole numbers as our subscripts for a formula, but for now this is fine. Zinc, phosphorus 0.5179, and then oxygen 2.066. So those were the mole numbers that we just calculated. Moving on to step 3, convert the number of moles in each element into whole numbers that become subscripts in the empirical formula by dividing each amount in moles by the smallest amount. Okay, So let's find the smallest amount. We've got 0.7787, 0.5179, 2.066. Well, clearly 0.5179 was the smallest amount, so let's divide all three by that amount. Okay, and when we do that, we'll come up with a formula of zinc 1.5, phosphorus 1, and oxygen 4. Okay, so still not complete. Sorry, this was step 3. Now we need to move on to step 4. So if the subscripts are not yet whole numbers, okay, that's the case for us, determine the least common multiple that will make the decimal values into whole numbers. Multiply all subscripts by this least common multiple. Use these numbers as subscripts to complete the empirical formula. This is the most difficult part of this whole process because we've got 1.5 for zinc. In order to convert that to a whole number, we're going to multiply all these values by 2. Okay, and we end up with zinc 3, phosphorus 2, oxygen 8, and that is our empirical formula for this material. Okay, so on a test you would want to write, therefore the empirical formula is zinc 3, phosphorus 2, oxygen 8 as your final answer. Now, when you end up, so this one we had, zinc came out with 1.5 moles, and that was a not too bad number. We just multiplied by 2, and that was okay. But sometimes you can get a bit of a weird number, and so you need to find the least common multiple that's going to create a whole number that's appropriate, and that can be difficult. So follow this if you run into that. So if you had carbon and then some mystery material X with a 0.8 mole, 0.8 moles there, what you want to do is basically recognize that 0.8 is basically 4/5. So if we multiplied that formula by 5, we could convert it into C5X4. Okay, here carbon and some mystery material X, 0.75. Recognize that 0.75 is 3/4. So if we multiply the thing, so here we multiply by 5. If we multiply this formula by 3, we're going to end up with C3X. Oh, I'm sorry. We're going to multiply by 4. And we're going to end up with C4X3. For CX 0.67, just recognize 0.67 as basically the fraction of 2/3. So we're going to multiply by 3, end up with C3X2. If you have 0.6, recognize that to be 3/5. Multiply by 5, C5X3. 0.4, recognize that to be 2/5. By 5, C5X2. 0.5, we know we've done an example like that, so that's going to be C2X. 0.33, that's 1/3, so we want to multiply by 3, C3X. 0.25, we want to multiply by 4. We're basically recognizing that as 1/4. We want to get rid of C4X. And 0.2, that's going to be 1/5. Multiply by 5, C5X. 0.17, finally. Recognize that as 1/6. We want to try to get rid of. Multiply by 6, and we get C6X.